All right, we're going to start off by doing Newton's three laws of motion in Unit 3. Covers a couple chapters, but we'll first go over, uh, well, we'll do them in order as they're written. And the first one will be Newton's three laws of motion will be, well, Newton's first law. It's probably one of the more widely known ones, as there are many of them that are, and some of them are very much inherent, and we have a good understanding of them. First off, we need to understand that what the definition of a force is. It's not a Jedi mind trick or anything that would suggest midichlorians. But it's any push or pull action. This is why a lot of times you've heard me say science can't suck, and that's because it can only push or pull in that sense, and that so any forces can be determined as a push or a pull. A vacuum does not suck; it pulls the air in through that. So, what is a net force? The net force is all of the forces acting on an object. This can become very complicated if we look at some things, as we'll look at it a little bit later. But we want to try and keep things as simple as possible. And it's if we add up all the forces that are involved. Again, we're going to try and keep things as simple as we can and not overcomplicate it, as we can very quickly overcomplicate things, and things can become a little bit harder for us to truly understand. The unit of force is 1 Newton. We've actually seen this before in some of our problems back when we were doing vectors and some of the math that is involved in there. And that's actually why you will actually see some of those problems again, is because now we can actually bring that into light. And so the unit of force is the Newton, is to give it his namesake of Sir Isaac Newton. It can also be expressed in this manner of kilograms times meters per second squared, which suggests that there's an equation that we might use to give it an equate of mass and acceleration. Those are some things that you would be able to look at and think about, but those for the most part are kind of what it is that force is a push or pull. The unit that we give it is in newtons. We'll get more into the actual equations that are necessary for that and to put on your equation sheet later on. As I said, a force is any push or pull that results from an interaction with another object. If the objects are not interacting, that means that there is no force between them. And that's a very important part of this. And that is like if you go and push on a wall, you are pushing on the wall. There is an interaction now. If the wall doesn't move, that means you're not pushing on the wall with enough force. If you push and the wall moves, that means you've overcome other forces that are involved, and then you are pushing with enough force for that object to actually move. For an object to change its velocity, there actually has to be a force involved. And because a change in velocity means that there's an acceleration. If there's an acceleration, that means a force has to be present. For your car to speed up, you have to press on the accelerator. That's what happens. That's what helps drive the car forward. It tells it whatever it needs. Now, going down a flat road, your car will slow down naturally. That's because there is something acting to oppose that you're driving. Friction, we inherently know that. We'll talk at more depth of that in part 2 or part B. And so therefore there is a interaction still. It's the wheels and the wheel bearings and all that other stuff goes into slowing of the car down because there is friction. Okay, there's an interaction. Anytime there is a force, there is an interaction. If there has to be, if there's no, if the object is not moving, that means there is zero acceleration, which means the net force would say that there is nothing there. And because forces can be written out with an arrow, we can utilize them for that, and that they are vector quantities, and so therefore we can have the both magnitude and direction components to solving some of these force problems. When the forces are balanced, that means everything is acting in opposite directions. You push on the wall pushes back on you. That's kind of getting into Newton's third laws, but for the most part, that's where you have. There is no change in motion because unless you do move something, but for the most part, there's going to be a certain amount of resistance to that. You go out and try to push a car that's in park down the road, you're going to find that that's very difficult to overcome that balance force. You have to really push with a lot of force to do so. To push unbalanced forces are meaning that the forces are that there is motion, there's something that's moving, and as you can see, the black arrow and the blue arrow make a bigger arrow, and therefore there is a motion, and we know there's a motion because the arrow's moving. The first example up here, this does not have any motion. This equals 0, and because there would be no motion, so it equals 0 newtons, or it just looks like on, and therefore you sometimes will put a slash there so that it looks like something else. We don't know what this is, but because we can add the arrows together, that gives us an unbalancing of our forces. One of the forces that we've talked about at great lengths is gravity. All objects feel the effects of gravity. They are an attractive force. It exists between all objects in the universe. Mass has a big part of it, and the distance between those objects. Now, we don't notice the attraction of why my pen doesn't just float around me and instead falls to the ground. It's because the more massive object is the Earth, and more massive objects are going to trump or negate any of the mass that I might have that makes my pen or pencil attracted to me. It's the Earth because it's so much more massive, and that's why it's there. Even though I am in close proximity to the pencil, it's still just because there is a much larger equation for this to actually show you how much there is. But just note that because of Earth, we don't have really. It's not very measurable. It can be, but it's not. It's pretty much negated because of that. Now, if you were as far away from any large celestial object, then objects would actually start rotating around you, and so you would have your own gravity, but even you would start to gravitate towards the next closest large object, whatever it may be, whether it be a planet or other celestial objects. But gravity is something that we definitely have to deal with and on everyday basis. Keeps us grounded. Air resistance is something else that is there. It's air friction is another way of saying it, but air resistance is something we all inherently know. It's why some vehicles will get better gas mileage just because they have less air resistance. They're more streamlined, and it is something that you can make measurements of, and that's what will help part some of those things. You can increase your air resistance by increasing your area of which the object has. If not, it is what you kind of have what you got. But the air resistance is that air exerts all certain amount of resistance. You stick your hand out of the vehicle a little bit when you're driving at 40 miles an hour, and your hand's going to feel that air resistance, or you can put it in kind of almost makeshift wing of a plane, and you'll see kind of the effects of that as well, and see how that air resistance works. Now, Newton's first law says that an object at rest will stay at rest, and an object in motion will keep moving at the same speed and direction unless acted upon by another force. In short, an object at rest stays at rest, and an object in motion stays in motion, unless acted upon by another force. But this is the longer drawn out as well. So in the example that we kind of have pictured here, this car would hit this brick wall. Okay. Now the person inside, because they're not wearing their seatbelt, would find themselves, when the car hits the brick wall, would continue to fly forward. Now, if they had a seatbelt on, that would allow that object at rest, and that would be the force to keep the person from launching outward, as we would not want. And these are why you shouldn't have things in the back of your car. Not that they're going to come and pummel you in the back of the head. You will not die by a tissue box hitting you in the back of the head. But there's just not good thing. It's just not a good idea. Is that anything that's not, so to speak, tied down is free to move, and therefore that's why you are putting a seatbelt on is more beneficial, and it works because of Newton's first law. It is that force that is acting upon you to keep you from moving forward and flying out of the car. A lot of times, Newton's first law is called the law of inertia. The more mass an object has, the greater inertia that it has. It's harder for an object to stop. If you've ever had to haul anything, say in a pickup, and you're driving down the highway, it takes longer to stop the pickup when it has loaded down with just a bunch of dirt. Say you have the back end full of dirt, it takes longer for it to slow down. That's why when you're on the highway, it's important that you give semi trucks more room to stop, because it is harder if they are loaded down. It takes longer for them to stop than, say, a small vehicle, and so it is important to have some of those parts and understand that that's what we call with inertia, is the mass that the object has. That's why when it comes to the name of the game, say in football, you want more massive players so that they have more inertia when hitting the other player as well. Speed also has a factor in this as well, but that's velocity. And you can look at some of the other things in there as well, because the more speed it has, the more mass it has, that means it's harder for it to decelerate, and therefore the inertia, it's resisting that change in motion. It's going to want to continue moving forward. But don't confuse inertia with momentum. Something that we'll talk about maybe later is the law of inertia. It deals with Newton's first law. An object's resistant to change in motion. An object that is in motion wants to stay in motion unless acted upon by another object. And an object at rest wants to stay at rest unless acted upon So an object, because of its inertia, its mass, will determine whether or not its ability to start moving or more resistant to moving. And so that's really what sums up Newton's first law of motion, is just that, kind of talking about law of inertia and some of these interactions that are necessary for a force to be observed. So as we continue forward, we'll do some more labs experimentation to solidify our understanding of Newton's first law.